Yeah. Sit down or sit down. Hey, good afternoon. Sorry you guys are not getting a break, but we'll get started in a second. Um, hmm? I don't- We're missing one person. Oh, we are missing Martin. Martin, where are you, Martin? All right, Martin one, come on over. Seat is ready for you. So, good afternoon, everybody. Can we get the presentation going? Um, I know it's kind of hard to be sitting there and listening to us, but hopefully the subject matter has been very interesting for you guys. As soon as we get the presentation going, we'll get started. In the meantime, my name is Mahesh Morjariam. I'm part of TerraBase Energy. I'll give you a longer introduction later. I'll also introduce a distinguished a set of speakers. You will soon recognize that they are really world-class experts. They have a lot of experience in renewable energy, in P2X research areas, in grid forming inverters, in energy storage, and finally, even more importantly, not more important, but importantly, the ability to actually have projects, which is EDF renewables. Can I have my presentation material? Oh, here it is. Great, thank you. And remote acts, uh, the last person walked away with it, perhaps. We have a lift off, I think. Okay, let's see. Um, Only if I can get it started. Okay, so this session, I think the folks in the, all right. This one is support, the other one. All right, sounds good. So the session goal is kind of indicated here. We want to discuss the topic of hybridization of multiple renewable energy sources. You have heard a great deal about them already, along with, more importantly, electricity storage, that makes the green energy production more cost effective. That's the main goal. So the topics we are going to discuss are challenges associated with intermittency. We heard a great deal about that, and variability of renewable energy sources, how hybridization and electricity storage solutions can play a vital role in balancing the supply and demand dynamics, and share some best practices. What you're going to hear from the experts here is some of the best practices in the technology sense, in the project sense, etc. With that in mind, let me just give you a brief introduction to myself. I'm EVP of Operational Technology at TerraBase. Previously, I was VP at First Solar for about 10 years, a lot of solar experience. And prior to that, I was with GE in wind energy, and so renewable experience. And I have a PhD in engineering. Not that you should hold that against me, but that's the thing. All right, and next we're going to have, and I'm going to introduce each speaker before they give a presentation. That way it's easy for you to remember who they are, etc. So I'm really pleased to present Dr. Raquel Garde. She's with the Senner Institute right now, and she's a senior researcher in the area of power to X technology. So she spent considerable time in this field. And so having her participate in this gives us an insight into the kinds of things that we need to be concerned about. She's responsible for energy storage group as well in the past. And she has more than 20 years of experience in renewable energy and hydrogen research. And finally, she has authored over 100 scientific publications and participated in international conferences. So really an outstanding researcher. With that, I will give it to Dr. Garde.
Yeah. Yeah, I think so.
About this.
Yeah. Yes, I can see.
It's hard to see the, sure, I understand.
Yeah. Yeah, it works. So, yeah, okay. So, good afternoon, everyone, and welcome to this session. In this short presentation, I just wanted to introduce or to talk about some two main aspects. The challenges that the hydrogen or green hydrogen production has to deal with due to the intermittency and variability of renewables, and the impact and the overall cost of hydrogen due to these challenges, and the potential solutions that we have to address these challenges. Okay, so I hope it's great. So what I wanted with this slide, I just wanted to show you the broad context with the hydrogen value chain. And I wanted to highlight that, well, the example is the main activities that we develop in the National Center for Renewable Energies in Spain, where I work, that focus mainly, can I point, is this one? Or mine? Well, it doesn't matter. If you see, we work very much on the development of different technologies, solid oxide electrolyzers, fuel cells, or power to X technologies. And, and this is something general, and that usually we pay very much attention to the technologies, and sometimes we forget a bit the, it doesn't work again? Yeah, we forget a bit the integration, the connection of these technologies with the grid or with the rest of the technologies in the value chain. So the main challenges regarding the green hydrogen production due to the renewable supply, this renewable supply has an impact in the levelized cost of hydrogen, as my colleague in the previous session from Dhaka, Morocco, explained very well. So it impacts very much the profile, the renewable profile, in the electrolyzer size, so in the CapEx, in the electrolyzer operation or capacity factor, or the number of operating hours, so in the OpEx. And so, well, as you can see in the figure, there are two profiles, one for a wind plant and other for a PV plant. So you can see the different capacity, the power capacity of the electrolyzer. And when we want to minimize the levelized cost of hydrogen, we have to achieve a balance between the electrolyzer size and the capacity factor. But when we want to maximize the amount of hydrogen produced along the year, then we have to, the priority should be the capacity factor. So, and for that, it is necessary to, or it is desirable, and smooth and more constant and manageable power supply. Also, the renewable or the variable renewable supply, power supply impact in the performance of the electrolyzers because of the dynamic operation. And it provokes materials and components degradation and continuous startup and shutdowns of the electrolyzer. So in the end, we have also an increase in the levelized cost of hydrogen. So to achieve, to achieve a balance between the electrolyzer size and capacity factor, and also a renewable power supply, stable and smooth, can lead or will lead to the most cost-effective and efficient hydrogen production. So these are the challenges. And regarding the potential solutions, so we have several, and I just listed some of them. We can use a combination of different renewable sources, and even the usual PV plus wind, but there are other renewables more manageable, even that as hydro power or geothermal plants. We can use energy storage systems, and depending on the scale, the amount of energy that we want to store and the time that we want to store this energy, we can use different types, even combinations of different energy storage systems. And we can use also the grid as a buffer. And in that case, we have to check very well, and we have to analyze in detail the different technology cases or the different renewable grid electrolyzer connection configuration. So to assess the feasibility of a power to hydrogen system, it is necessary to analyze in detail the different possible connection configurations of the electrolyzer to the grid and to the renewable sources, taking into account the renewable characteristics of the site or in the project, and this analysis usually are done in a case-by-case basis. So I think this is all from my side.
Thank you so much. I appreciate. Let me see if we can continue on. I switched. Okay, so next we have Martin Guan from Huawei. He's a solution director at Huawei North America, Africa South Smart PV. He's worked in renewable industry with Huawei in very many different regions. He's involved in development of solar projects in Morocco, Tunisia, Senegal, Burkina Faso, and Ivory Coast. I guess you haven't left any other country yet, have you? You still have how many? 50, 40 some countries more in Africa to go through? Okay. Commissioning, and he has been commissioning engineer for, Kingai, Santala 2.2 gigawatt project. So quite a large one, and one of the largest ones. And also with the Navoy 100 megawatt project, the first solar project in Uzbekistan. So quite a range of things that he has worked on. It's really a pleasure to have you on.
Yes, thanks for your introduction. So thanks for introduction, and dear distinguished guests, good afternoon. My name is Martin. I'm a solution director of Huawei North Africa Smart PV team, and it is my great pleasure to have this chance to stand here and share some ideas about how PV and storage solutions support the gray hydrogen production. So when we talk about gray hydrogen production, I believe the key or core points is to how to guarantee the hydrogen production is 100% green. And so when we utilize the grid electricity to power the hydrogen production equipment, there is always doubt that is the gray is the hydrogen production is 100% green or not. And today I would like to bring some ideas to utilize the microgrid solution to power the hydrogen production equipment in order to realize the 100% green hydrogen production. And sorry. In fact, microgrid solution is a very promising technology in the future network. And it consists of, firstly, of course, the renewable resources such as PV and wind. And secondly, it consists of the battery storage system, which provides the grid forming capability to form a strong enough grid to carry the load of the loads such as hydrogen production equipments. And Huawei, as a technology leader in the renewable industry, in fact, we have already studied in this field for a very long time. And last year, we have already launched the first generation of microgrid solution. And today, I would like to share some advantage, or can say unique solution of Huawei, what we can reach in the microgrid solution. Firstly, it is about scale. And Huawei is the first company who can realize, who can provide the solution to support the over 100 megawatts level microgrids. And secondly, I would like to share about the reliability capability of our microgrid solution. As you can see that this is some overview map of a microgrid solution, and it consists of the renewable energy source like PV and also the storage. And the key point of the whole system of the microgrid, it is about reliability. Why? Because compared with the normal grid, or can say the main grid, microgrid is always weak and has a problem of the, or can say the defects happening from the grid. And if your system, your battery storage system, or your renewable power, renewable PV system, or can say wind system, cannot support the stable operation in the weak grids, and then the system is very vulnerable and is easy to be breakdown. And so in this case, based on the long time research experiences of Huawei in the grid compatibility of the renewable resources, Huawei has developed a very comprehensive solution to support the weak grid fault rise through, and to support the whole system to stable operation in the very weak grid scenario. For example, like when the SCR ratio of the grid down to 1.1, Huawei's PV solution can always, to stable operation. And the last part I would like to introduce, it's about the safety. So you can see that in the microgrid solution, the key points, or can say the key equipment, is about the storage system. And when the developer, when they develop the storage system solution, the first priority is always about safety. And Huawei has already put this safety design concept everywhere in the production line. So firstly, when we talk about the selection of the raw material, Huawei has a very strict and comprehensive selection process. For example, for the battery cell, we will do the squeeze test, we will do the drop test, we will do the penetration test for every brand battery cell, and to select the most safety and stable brand, battery cell for our products. And secondly, it's about the system design. So for Huawei battery container, we have a multi-level protection from the battery cell level, battery pack level, we have the battery pack optimizer to realize a fault isolation between different battery module. And we have DC-DC rack for 6 racks per container to have the rack level shutdown and the rack level protection. And then last, it's about the container level, the whole system level. You can see that from the hardware, we have multiple protection. And besides the hardware protection, Huawei solution also has some software which we can load it in the cloud battery management system to help the system to do the prediction of the potential risk of the whole battery system. So we have a case nowadays back to China, and during the long time operation of the battery cell, and the battery cell has internal short circuits. And this situation during the daily inspection, or can say operation and maintenance of the battery system, for them, it is very hard for them to identify it by eyes or by the visual inspection. And it depends on the software like Huawei developed. We developed AI technology to detect the circuits of the battery cell to identify the potential short circuits from the normal battery cell operation. And then we can do the 1 day in advance alarm for our clients to identify the internal short circuits of the battery storage system. So you can see that Huawei has already put the proactive safety design concepts everywhere in the production or design of the products. Although you can see that the microgrid solution, or can say the energy storage solution, is well developed in the past few years, but there is always discussion about the economic parameters of the microgrid solution. And today I would like to bring some ideas, or can say some experiences from Huawei side regarding to the microgrid economic parameters. So at the beginning, when we calculate the economic parameters of microgrid solution, we always compare it with the desire generator. Why? Because desire generator is the most traditional microgrid solution, let's see. So when we compare the current microgrid solution between the PV and storage and the desire generator, you can see that definitely because desire generator has a very high levelized cost of electricity, up to 13 US cents to 15 US cents in Africa. And when you calculate the microgrid solution with renewable sources and the battery storage, you will have like 10 cents or 15 cents per kilowatt hour for the levelized cost of electricity. So you will have the ROI like 3 years to 5 years compared with the traditional desire generator. But I know that if we look at the green hydrogen production factory, we must to compare the microgrid solution with normal electricity price from the grids. And then we have the challenge. But like I mentioned, firstly, with the development technology of the battery storage system, we can see that before we have the battery cell from 218 amp hour, 320 amp hour. Nowadays, or in the future, very soon, we will have like over 400 amp hour battery cell. So with the technology development, I do believe that the levelized cost of electricity of the microgrid will decrease gradually. This is first thing. Secondly, regarding to the raw material price of the lithium battery. As we all know that in the past 1 or 2 years, there are some fluctuation of the raw material price of the lithium battery because of the shortage of the raw material. But if you look at the whole trend of the lithium battery, we do lithium battery price. I do believe that the raw material price will decrease very fast in the near future, and we will have a better levelized cost of electricity. Yes, and last but not least, I would like to emphasize that we cannot ignore also the extra value where the microgrid solution can bring to the developers. Let's take an example of the Saudi Arabia. So in Saudi Arabia, according to our calculation, based on their carbon tax policy, the microgrid solution can help to save like 10 million for only 10 megawatt lots in 20 years. So carbon tax, I do believe this is a concept that we will be very familiar in the near future, because the European League has already, the European countries have already launched the related policy regarding to the carbon tax. And so that's some understanding that I would like to share regarding to the economic parameters. And the last part I would like to share is some practical references related to Huawei in the microgrid solution. In fact, back to last year, we have already delivered the world's largest microgrid solution in Saudi Arabia. For it is RASI project supply which consists of 400 megawatt PV and 1.3 gigawatt hour storage, and supply 100% renewable energy for 1 million people in Neom City. And this is, I do believe, in this project delivery, Huawei, in fact, we didn't play only as an equipment supplier. In fact, from the very beginning of the design of the project, Huawei supports the simulation of the project. And because at that time, the microgrid solution is not very mature. And in order to verify the simulation of the whole grid system, Huawei also built 8.8 megawatt hour pilot system in our laboratory to verify our simulation is correct and our solution can support this grid. And then during the delivery stage of the project, Huawei engineers go on site and to provide different tests for the whole system. And till today, even we have already supported the commissioning of the whole project. Till today, our engineers, our experts are still on site to test the different situation happening from the grid and how the system will react to those defects or faults. And I believe that Huawei now is the only company in the worldwide range who understands the microgrid solution well, because we have the real situation, practical experiences in this RASI project. And thank you for your time today. That's all my presentation.
Thanks a lot, Martin. We appreciate it. As you can see, there are a lot of solutions available for off-grid, microgrid kind of situation, and integrating with storage, and quite a lot of advances done in power electronics, which is great. Appreciate that. Moving right along, again. Next, we have something more on storage. Alan Greenshields. He's a director of Europe at ESS Incorporated. He has over 15 years experience in rechargeable battery space. He has founded and ran several technology ventures in the UK, Germany, and Switzerland. So quite a track record as such, and involved in think tank on energy, environment, and business strategy. Initiated by Harvard Business School in 2010. So with that, Alan, I will let you go. He has an MBA from Harvard Business School as well.
See if I can get the microphone to work. Okay, it works. Yes, it's interesting to think back to 2010, because back in 2010, people were saying, if only wind energy was dirt cheap, if only solar was dirt cheap. And back then, people were saying, it's never going to happen. And in fact, it all happened, and it happened to a degree nobody ever thought was possible. Back in 2010, part of the members of the same think tank were major US utilities saying nothing will ever be cheaper than coal, nothing will ever be cheaper than gas. And it only took about 10 years. In fact, a lot had changed. So my interest in the space has always been, we need new technology to get the cost down. And specifically the area of storage. Storage is an enabler for many things, because to cite some people from the US Department of Energy ARPA-E project, there's only three things that matter in storage: cost, cost, cost. And if you think about the discussion today and go to the other extreme, if storage cost nothing, then basically we wouldn't have any problems. You'd have ubiquitous storage everywhere, and when you need energy, you dispatch it. So the answer is basically thinking what needs to happen. We need super cheap storage. I'm working with ESS, which is an American company. It's actually a graduate of the ARPA-E project. And in the quest for very cheap storage back in 2012, there are a lot of activities done to look at the very basics of storage from a fundamental point of view, simply whatever you're using to store energy, how much does that cost in relation to the energy you're storing? What is the fundamental material cost in that? So out of that focus on iron, why iron? There's lots of it on the planet. It's very cheap. It's not a compromised material. You can source it on any continent. And the question was, can you develop a technology using iron as the active material for bulk storage of energy? And that's exactly what ESS have done, and that's exactly what they now have succeeded in from a technological point of view, and are now commercially shipping product based on the system. So I'd like to say a few words about what the technology, how the technology works. If we could maybe move to the next slide. So for the, this is a schematic of a small system, and a flow battery is a very different type of concept compared to conventional lithium cells or other cells. In a lithium battery, you store the energy in the electrodes. You're basically, as you charge and discharge, you're shuttling lithium ions between two electrodes at different potential. That's the energy storage mechanism. Well, what that means from a cost point of view is that the capacity of a cell is directly proportional to the mass of active material in it. If you want to double the energy capacity, you need to double the kilograms of active material. In a flow battery, the energy is stored in the electrolyte, or rather two electrolytes. You have two electrolytes forming the two half of the battery, and the concept, the concept got a lot of interest for long duration storage, bulk storage, because unlike a closed cell system, you have a reactor system, which has a fixed cost, and the capacity of the battery is determined by how much electrolyte you flow through the system. If you want to double the duration, you flow twice the electrolyte through the system. That's an underlying principle. So I won't go into too much of the chemistry, but the interesting thing about the ESS system is that both of the electrolytes are the same stuff. They're both ferric chloride, FeCl2. It is a very simple, non-toxic, non-flammable material. Even in a place like Germany, it's considered to be harmless to groundwater. So it is a very good place to be from a permitting point of view, from putting batteries next to buildings in towns and places where people worry a lot about safety. And what you see in the rest of the system is it's more like a small chemical factory, because what you're actually doing is pumping electrolyte through the reactor system to charge and discharge energy. So it's a very interesting approach. And this is actually available in commercially now being manufactured in the United States. If we move to the next slide, just some of the current parameters of that. At the moment, we're producing up to 12 hours. Why up to 12 hours? It's not, that's an interesting design choice. If you run the numbers on what full decarbonization means, you need three things. You need short duration storage, you need intraday storage, and you need something like hydrogen for longer periods. Those are the three buckets you need to fill. And with 12 hours, it fulfills one important thing: you get to tomorrow. And if you run the numbers on that, that's roughly, for full decarbonization, is about 80% of the storage you need is cycling energy in a 24-hour frequency, and reflecting the pattern of activity on Earth and the pattern of sunfall and these kind of things. The technology has a very low levelized cost of storage simply because iron is cheap. And cheapness is a key parameter as we discussed before. One thing which is unusual for flow battery, it's a fast response system. So if you're building microgrids, which I wholeheartedly agree are one interesting thing to do, if you have a 12-hour ESS battery, that battery can also do frequency and voltage regulation inside the system. And one of the other interesting things about a flow battery, it's not a closed loop system. It's an open system, which means if you worry about things like chemical changes in the system over time accumulating to degrade the system, you can do something about it. And that's exactly what a lot of what ESS's intellectual property is about, is how do you keep the electrolyte conditioned so you have no capacity fade, no power fade, and no energy losses over time at all. I think in the interest of time, I'll just go straight to some of the sustainability properties of the battery. Made out of iron, nobody panics about that. It's a cheap and safe material. What we're seeing is huge interest from people. We're often asked about are batteries in competition to hydrogen? The answer is no. The answer is the storage task we have is so huge, anything at all that commercially can store energy, we need all of it, and as much of it as we can possibly make. And on the contrary, anywhere where you're building a large capital intensive asset, which is being operated by renewable energy, the economics are almost certain to be better if you add storage to that system. So my answer to these questions is it's another tool in the engineer's toolbox for improving the overall system optimization, and the specific optimization will be different in every use case. But certainly for generation of hydrogen, if you're investing a lot in an electrolysis system, your uptime, your utilization will be a significant factor in your overall cost. If you can add a battery to the system to bulk store energy, then it's likely to have better economics. I think we go to the next slide. So just to give you an idea of what we're doing with the technology at the moment, we are actually doing, it's not quite in the scale as you're planning in Morocco, but with LEAG in Germany, it's a very large traditional strip mining and coal generation company in the eastern part of the country. They are building 14 gigawatts of renewable on former mining land. And there we're basically building exactly this mixture of short duration storage, long duration storage, and hydrogen on the site of a former coal-fired power plant. And our piece of that is to deliver a 500 megawatt hour iron flow battery to be operational by 2027. But we also have some microgrid applications, airside operations at Schiphol Airport. It's an unusual case, but in fact, all of those little diesel generators on airports collectively produce a huge amount of soot and CO2 and other things. So in fact, this is to enable electrification of all of the things which are currently done with diesels. SMUD is one of the Sacramento Municipal Utility District, is one of the most forward-looking utilities in the US. They actually have a goal of net zero by 2030. And as part of that, we are working with them to deploy 2 gigawatt hours of storage in their grid. They're a cooperative, so it means they're a not-for-profit cooperative, but a very large utility. And with that, the energy storage, in fact, was really the last piece of the puzzle to enable them to fully decarbonize by 2030 without significantly putting up energy prices, potentially reducing them. So I think at that point, I just stop there because I could
Thank
give
you
you an
so
idea
much.
of the
We appreciate it. Thank you. As you can see, there are a lot of developments going on in storage, and it's really critical that we continue to drive down the storage cost as well, because if storage is free, as Alan says, then we would have actually solved this whole renewable intermittency issue very, very easily. Next, would like to have Modest Kwapinski. He's EDF Renewables he has been with EDF Renewables from 2014. He's currently the CEO, EDF Renewables Morocco. And he's overseen a successful construction of the Taza Phase 1 wind farm, the financial closing of Claudia Albaida wind farm, etc. So you can see he has been involved in numerous wind farm and projects, renewable projects, solar storage, etc. Previously, he was with U.S. Department of Justice from 2010, served as a legal advisor based in American embassies in Congo, Senegal, Tunisia, and finally in charge of North Africa, including Morocco. I guess you're also making the round of all the countries. Got quite a few to go, by the way. And has an international economics law degree from Georgetown University in Washington, D.C., and also degrees in economics and law from University of Florida. With that, I'd like to give it to you.
Thank you, Mahesh, for that kind introduction. I'm going to try the lectern, actually, in case it doesn't work. Good afternoon, everyone. It's a real honor to be a part of this very prestigious event in Marrakesh, as well as be one of the panelists on this distinguished group of experts. Thank you again to the organizers, ESN. I know it wasn't an easy decision to greenlight this conference. I think it's a really important decision that they took for all of us gathered here that look forward to this event, but more importantly, to the many people that rely on this event for their economic well-being. So there's already been a wealth of very good presentations from my colleagues in the panel regarding some of the leading edges of where technology stands today, where engineering is leading us. I'm not an engineer, as Mahesh pointed out, but perhaps what I'd like to do is add a little texture to the already excellent presentations and give a little perspective from the ground, since we've been a player in Morocco for now over 10 years. And we have specifically two projects that leverage hybridization in order to drive costs down and increase value for our end customer. So perhaps I will start by introducing our company. The other way. Okay. So EDF Renewables Morocco is the company that I represent. It's a wholly owned subsidiary of EDF Renewables, which itself is wholly owned by the EDF Group. The EDF Group had an annual turnover of 143 billion euros last year. Its generation mix of 123 gigawatt net installed capacity is one of the greenest on the planet. Last year, 90% of our electricity production emitted no CO2. 90%. So out of the total production mix, 36 gigawatts of renewables in about 25 countries positions EDF as a leader in France, a leader in the European Union, as well as position number 5 worldwide. If you focus on the non-hydro generation, our mix is 11.4 gigawatts net at the end of last year, which is roughly represented by 66% onshore wind, 28% solar, about 4% offshore winds, although that balance is approaching more of an emphasis on storage as well as offshore wind. So I'd like to now move to an emphasis on the Middle East and Africa. We're today one of the dominant players in the region, having won in the last 5 years roughly 4 gigawatts of public tenders, mainly in the Middle East, including the world's largest PV plant at Al Dhafra in UAE, as well as the region's largest wind farm in Dumat Al Jandal in KSA. In Morocco, we're extremely proud to have celebrated our 10-year anniversary last year. Coincidentally, it occurred at the same time as the end of construction on our first wind farm, which was phase one of a 150 megawatt site at Taza. We also reached financial close on Kudi Al Baida, which is a project that we developed with Mazen in a public-private partnership that is the first wind repowering project on the African continent, something that we're particularly proud of. So basically, we took 90 machines that produced a total generating capacity of 50 megawatts. We doubled the capacity, and we reduced by 80% the number of wind turbines. So that is a project near Tanger. And then specifically on the topic of hybridization, EDF Renewables, alongside its partners Masdar and Green of Africa, right now have initiated discussions and very intense work with Mazen to bring back the Normidelt 1 project. We're aiming to reach financial close on that project sometime end of this year, beginning of next year. It's the first large-scale hybridized renewables project in Morocco. It relies on classic PV, it relies on parabolic trough CSP technology, as well as batteries, of course, to ensure 5 hours of injection of electricity after sunset. So on this project, I think it demonstrates quite clearly that mixing hybridization in a way that creates value is really the way to go. We have on this project significantly reduced capex and therefore the tariff for the off-taker, as demonstrated by the significantly reduced costs when you look at a fully hybridized project like Normidelt versus some of the other CSP projects both in Morocco and worldwide. So specifically in terms of green H2 and its derivatives, EDF deployed a strategic plan last year in 2022 to reach 3 gigawatts of electrolysis by 2030. Specifically, 1/3 of that, 1 gigawatt of electrolyzer capacity, is going to be based in the Middle East to mainly produce competitive green ammonia, mainly for export to the Asian and European markets. Besides Egypt, Oman, KSA, and UAE, we're obviously relying upon our efforts in Morocco as a main pillar of this H2 ambition. So here we have the conceptual design of phase one of our Gelmim project, which in its full phase will be 500 megawatts. It is backed by 1 gigawatt of renewable mix from wind and solar, as well as batteries. The end product is 350 tons of green ammonia per day, which, as I mentioned, we expect to ship for export, although we'd love for there to be a robust local market, which would help as well drive down costs and make a more competitive LCOH. And it's a bit simplified here for the purposes of time, but basically here we have indicative figures of the planned one phase as a way to show that how we have tried to optimize some of the excellent resources, no doubt, in Gelmim, with the leading renewables technology to produce the most competitive H2 that we can engineer, which is, of course, competing not only with other players in Morocco, but as well other countries that are positioning themselves for export. So here in the first column, as you can see, in spite of its excellent solar resources in Gelmim, we still only get a load factor of 39%. Wind alone in column 2, also very, very good in Gelmim, gives you a load factor of 52%. However, your aim as a developer has been mentioned in this panel and the one before that, is to reach the highest renewables-based load factor. It's been mentioned time and time again. It's to reach criteria for green H2 certification, particularly if you're positioning yourself for the European market, but also to achieve the greatest quantity of H2 per capex, your LCOH. So if we look at the third column, we combine solar and wind, which certainly helps address some of the intermittency issues, resulting in more stable energy supply. Here, 77% load factor. Then you add in the batteries, charge, for example, from oversized solar plant in Gelmim, which effectively begins to decouple the H2 from some of the intermittencies and variable nature of renewable energies. And you see this incremental improvement in load factors, yields, and LCOH as well, that improves for each incremental load factor, resulting in cheaper H2 and cheaper green ammonia. So one final thing that we're looking at in Gelmim to drive down the LCOH, we're looking at other roads to market, such as selling excess electricity as a grid service, as well as using corporate PPAs under the 1309 regime to try to share some costs and build some revenue, driving down the overall cost of the project. So I think I've run out of time, but again, just to say we're very, very bullish on Morocco. We're very bullish specifically on the Gelmim region. The resources are excellent, as many of you know already. The sort of complementarity of the resources in Gelmim make it an exceptional area. And so a lot of you developers out there are looking forward to hearing more about the Offre Maroc, and we hope it really adds the policy incentives necessary with already wonderful natural dispositions to really lead and push Morocco into one of the top H2 producing countries in the world. So thank you for your attention.
I'm just going to spend a few minutes to just summarize some of the material that you heard about. By the way, I'm with Terra-Base Energy, and one of the things we do is modeling work and design work. And part of this is the effort to essentially figure out how do we optimize the plant. So the main message I want you to leave with, not that you haven't heard that many times, is that utility scale PV and wind have reduced costs, in fact, significantly over the past couple of decades. Wind in the 2000 decade, solar in 2010 decade, almost 90% in each case. However, there are intermittent resources. So what we have to do is figure out how to deal with them with the electrolyzer as well. Now, the thing to bring up is that electrolyzers have also becoming much more attuned to be variable resources as well. So it's not the case that we have to have completely firmed up power all the time. And then finally, the modeling work we can do is to figure out exactly how much resources we need of each kind, the size of each kind, in order to make that most cost effective. And as was mentioned by Martin, grid forming inverters is a new technology that's coming in that will help as well. With that in mind, I'm just going to share with you some of the modeling work we do and figure out what size of PV plant should we worry about. And this is mostly in the off-grid situation. How about the wind plant size? How about the size of the electrolyzer? How about storage? How much storage should we have? If we have too much, then it costs a lot of money. If we don't have enough, then it has intermittency and so forth. So what we do is basically to look through all these variables, have a very detailed model, and use that to figure out how do we optimize the plant configuration. Stuck on a graph that I was trying to be fancy, but okay. Can you just press down button or something? Yes? Okay. No? Don't. All right, never mind. Anyway, with that in mind, I think the time has gone and it's like really late for all of you. So I want you all to give another round of applause to our wonderful speakers. As you can, and thank you for your attention. We wish we had more time for questions as well, but everything is kind of contracted. So, but feel free to stop any one of us if you have specific questions that you would like to address. Thank you.